I want to continue here with this introduction into thermodynamics. We were at the very beginning still, but just to take up, I started to introduce mechanical work, and probably you know that at least for gases, the mechanical work which is performed by a system is given by minus PdV. And just keep in mind that if you have other systems than gases, this term becomes more complicated. Yeah? So it's sigma d epsilon, which replaces this simple pressure and volume. But for the moment, that's sufficient for us. Also, if you have magnetic systems, you have BdH, which gives the magnetic energy or magnetic work, which is performed by the system, and so on. So you have to figure out which type of system you have. And then already an important step is if you, this is something one has to get accustomed to, but I show it first. If you keep the pressure constant instead of the volume, so we want to change our system on a consideration from one where we control the volume or keep the volume constant to one where we keep the pressure constant. Yeah? Which is very often the case. Yeah? I mean, think of a solid. It's very difficult to keep the volume constant, but much easier to keep the outside pressure constant. So, and there's a simple mathematical trick. We write down the internal energy from above, which was delta Q plus delta H, and we put this PdV here. And this already, did I put my pointer? Ah, here. This already shows here, these little d's, they tell you which variable I use to control the state of the system. Yeah? So I look what happens if I change volume by a small amount. Then I change the internal energy, for example, here. Now I want to, instead of changing the volume, I want to change the pressure or control the pressure. Yeah? What can I do? I rewrite this to du plus something. Now I want to have something plus dp. Yeah? So what I do is to add p times v. If I do so, I have du plus pdv plus vdp. And du is delta Q minus PdV. That's this one here. And now I have plus PdV minus VdP. And this cancels out. So what I obtain is delta Q minus VdP. So this is a case where I can look what happens if I change the pressure by small amounts, dP, and then this changes this quantity here by a considerable, by a corresponding amount, and this gets a new name. That's the enthalpy. Probably most of you know. In this way, you can step by step replace quantities by other quantities to get other free variables, and more or less to also change the ensemble in which you work. We will do the same later on for the temperature. But before we have to introduce the second law of thermodynamics, which is a bit more complicated than the first one. Did I make a mistake here?
No,
Yeah.
I'm wondering
Yeah,
why
right.
there is a minus sign in front of VDP.
Must be this way.
Plus,
You're right. I just want to get rid of the minus PDV here.
yeah.
So that's, of course, I have to take a plus here, and that's a plus here as well. Sure.
You have a question?
Yeah?
So this enthalpy, now in general when we talk about enthalpy, it will also have the latent heat. It will have sensible plus latent. And later on we will use this equation for phase transition.
Yes. What is your...
Enthalpy,
Yeah?
latent heat of
I mean,
fusion.
yeah, basically the difference between internal energy and enthalpy is whether you keep the pressure constant or the volume constant. Normally for solids we say does not matter too much, yeah, because it's a simple case. If you keep the volume constant and you heat up, for example, or go through a phase transition or whatever, you keep the volume constant. This means that you have a large, or perhaps you have a large you would have a large expansion of your volume, yeah? But you don't allow it. You keep it constant, yeah? If you keep the volume constant. And that's a part of energy which you can, in principle, use later on by letting expand, yeah? So, and if you keep the enthalpy constant, this means that you already allow for this expansion. So this is basically the difference. But since most solids have small coefficients of thermal expansion, this difference does not matter too much. But if you work with gases, for example, the difference is huge. As you said, the specific heat at constant pressure minus the specific heat at constant volume is, what is it, R, I think, the gas constant per mole. Yeah? So there is a considerable difference. I think there is a, how is it? I mean, playing around with all these thermodynamic quantities, you can set up a relation between coefficient of thermal expansion, what else was it? Specific heat and one further.
Molar volume.
Huh?
Molar volume.
Yeah, that's a volume, but there is a third quantity. You get a similar relation like the one for the gases, but much more complicated and less known.
U plus PV is generally sensible internal energy plus flow work. Flow work. The PdV term
Yeah.
and VdP.
Mm-hmm.
So physically internal energy plus flow work we are addressing in
Right.
enthalpy.
Yeah.
But this equation is also valid for melting or any phase transition.
Sure. Yeah. I mean,
So how we can reflect at this stage?
I mean, as soon as you have changes in volume, yeah. If you keep volume constant, you suppress these changes in volume. Yeah? For example, if you have a phase transition with a change in specific volume, say you melt ice in a constant volume. As I said, people here are not so familiar with ice, but no, if you freeze something, you risk to destroy your container. Yeah? If you have a closed bottle and freeze the volume inside, you build up large stresses because you do not allow for the volume expansion. Yeah? While if you have a free surface, then it can expand, and this part of energy which built up the stress can, I don't know, escape. Okay? But in this case, of course, it's important, but since volume changes often are not that large in solids, often we don't care for it. But I wanted to skip over to the second law of thermodynamics. I showed this example of the pen falling down but not jumping up. Yeah? Despite the fact that it does not violate the first law of thermodynamics. And there are many processes which could take place without violating the first law, the conservation of energy, but which do not take place. There is this famous, what is it called, Maxwell wheel. You imagine a small wheel with kind of wings, yeah, and a kind of ratchet, so it can rotate only in one direction. And now you let molecules hit these little wings. Yeah? In one direction, it can rotate. In the other direction, so you have the ratchet which prevents rotation. Yeah? And the question is, did I construct a perpetuum mobile or not? And of course, the answer is not. Everybody knows this is not possible. But why doesn't it work? Yeah? And many of these molecular engines, biophysicists currently are working on, more or less rely on these principles. So why isn't it possible? The answer is that these ratchets also consume energy, and if I make it smaller and smaller, I have also thermal fluctuations which prevent this ratchet to work. So this perpetuum mobile is not possible, and the primitive answer, because it violates what I come to, the second law of thermodynamics. So the question is, why does my pen, which fell down, does not take up the energy it put into the floor before to jump up again? Even if they don't violate the first law. Don't violate. So energy conservation is okay, something else must be there. And the answer is there is a second law, the title says. And basically it would mean, so for example for my pen, from the ground I don't go through all the details, but basically it says that a certain quantity S in a closed system is always increasing. Constant. That's very important that we consider closed systems, because often people ask, I mean, humans like us here, we are in a state of very low entropy. How can this be? And this can only be because we always get energy from the outside. If this influx of energy stops, then our entropy goes up, which means that we die. So the ds is larger than 0. And I don't want to explain this, but this is this famous statement from my professor from before. Q is not a state function. But S is, and ds equals delta Q over T. And this means if I do this, if I would do this integration from one state to another state, if I would integrate the heat along this path, I would get something else as if I would go along this path here. Yeah? Because it's not a state function, yeah? And I can produce heat or more or less. But if I, at every point, if I determine the temperature here and divide these little steps in this little, say, additions in heat by the temperature at this point, then I get a precise quantity which is independent of green or red paths. Yeah? So this is, and yeah, stay here. If I go from here to here and back here, this means that I go a closed cycle. I stop where I started. So I have a, what we call a reversible process. I go back and forth. And this does not change the entropy. Yeah? So for a reversible process, and vice versa, if we have an irreversible process in a closed system, ds is positive. Always in a closed system, yeah, of course. We come to a better interpretation what entropy really means in a moment, yeah, or maybe not in a moment. I don't know how much time I'm given. So if you look for a reversible process, we have this ds equals 0. And you know that the amount of heat I put in or get out is proportional to the specific heat. CV. Or at constant pressure, you have to replace CV by CP. And this allows then to determine entropy changes. to integrate if we have such a situation. So for example, if we want to go through a melting transition and you want to calculate the whole change in entropy, you can integrate along the temperature axis. Here's the internal energy, which is a derivative of CV is a derivative of U with respect to T. You have something like this here, for example, in a phase transition. So you integrate here, and this delta U. It's a phase transition. And then to obtain the S, you can just integrate here using the CV. You get something similar here. I did a little calculation how much this pen, this falling pen, would raise the temperature and how much temperature how much cooling it would require, but I think I skipped this. It's 3 millikelvin if I assume a 10-gram pen falling from 50 centimeters high and so on. So you can do all these calculations, and you can also calculate the change in entropy. I came to, what is it, 15, I can't read my own letters here. Millijoule per Kelvin or so. At least it's positive. A more instructive example is if we look at the expansion of a gas. We first put it into 1/2 of this container. And the other half is empty. And then we open this barrier in between. And let the gas expand in the whole volume. We assume that this takes place isothermally. So at constant temperature, we can control the temperature. I assume that this is volume 1 and this is volume 2. So the internal energy then does not change, which means that delta Q equals PdV. So our delta S now is the integration from V1 to V1 plus V2. delta Q over T. I assume that T is constant. Also consider more complicated situations. I can take it out if this is constant. Delta Q is PdV. And we assume that we have an ideal gas. I forgot. With this law of gases holds PV equals nRT. And the number of moles. The gas constant. Kelvin. Then we can do this integration. We replace P by nRT over V. You see, T cancels out, nR, and then we can do the integration dV over V is ln V divided by V1. And at least you see that this is a positive quantity. Oops. You see that my pointer does not work anymore. So it's a positive quantity. The logarithm of a number larger than 1 is positive. So we have a positive change in entropy, which tells you that this process is irreversible. Yeah? So by pulling out this wall, the gas expands. I mean, this is something everybody knows from experience, from daily life. The gas will never go back into this left half here. It stays distributed over the whole volume. This was a question when all these models were developed, and especially when this atomistic view on all these systems came up in, I think, 19th century. Why don't all the gas molecules in a room, why don't they all assemble in the corner? Yeah? I mean, in principle, this would be possible. As we will see, this fortunately never happens, or at least not in our life. And here's part of this explanation. Yeah? And this also goes over to the last part, which is very important also for the application in atomistic simulations. That's the statistical interpretation of entropy. Until now, I introduced this entropy just as one more thermodynamic quantity. Nobody knows really what it means. But it has a very precise meaning. And this meaning goes back to, let me see here, to a famous person, which is seen here. I guess you know who it is. It's a grave of Ludwig Boltzmann, an Austrian physicist, I think. And above here, you see engraved, I think I have it enlarged, this famous law he derived, which is given here, S equals K log W. They omitted politely the sub B. This K now is called Boltzmann's constant, KB, and very often we speak of KB instead of K. I can come to this in a moment, what it really means. Basically, we already saw it in this example of the gas which expands. If we look to it from another point of view, we can say if we expand this gas, we lose some information. Yeah? Before, here in the first situation, we know all gas molecules are sitting on the side here. Depending on from which side I look, it's this left or right side. All are here. Afterwards, I only know that they're somewhere here. So I lost some knowledge. That's one point of view, and that's why entropy is also very important in information technology. Yeah? They also speak of entropy, so for example, if you transmit data or so, yeah? Or if you encrypt data. Or we can say, if we pick out a particular molecule, one of the 10 to the 23 or so, if I pick it out here, I know it's sitting on this side. If I pick it out here, I know only that it's sitting somewhere here. Yeah? So the probability to find this particular molecule on the left side is only 1/2 if both volumes are same size. Yeah? So entropy describes our non-knowledge or the probability for a certain event to take place. I put it in quotation marks. And other way around, it means it measures the probability of a certain situation. Yeah? And the second law of thermodynamics, that entropy normally increases, just means, in a very simplistic way to say it, that things go to the more probable than more often as they would go to the less probable. Yeah? So I said this probability to find a certain molecule in V1, I call this W1 is equal to 1. And afterwards, it's only the ratio of the volume. Now, if you have n molecules, which are assumed to be independent. That's the case for an ideal gas. Then the probability just is a product of the single probabilities. Oh, I want to use a uppercase n here. And for example, we can use 1 mole of gas, and we have this number of molecules, just the Avogadro number. And since these are huge numbers, it's often practical to use the logarithm. So for the situation before, maybe I should put 1 or 2, 1 and 2 here. Equals 0 here. And after, when we opened this wall, we have our probability here to the n, to power n. So the logarithm and now if we compare this result to the one above here, sorry, I should not point here, to this one, we see a certain correspondence, resemblance. If we assume that we have 1 mole, this would mean lowercase n equals 1, uppercase n equals Avogadro's number. And things get even a bit simpler. So we can equate these two, or can replace this logarithm here by the other one here. And we find that this delta S here is what did I do here? Okay, I forgot. I need one further step. R is the Avogadro number times this constant I already mentioned. And then we can bring everything together. I think I shift this down a bit. So delta S now becomes our lowercase n is the number of moles divided by the Avogadro number. R is Na times Kb. And then we have this ln here, which I want to replace here, which is just a minus sign. So it's 1 over n minus ln Wn. And if we put all this together, we find this famous law going back to Boltzmann, that the entropy change between two different systems or two different states is given by the logarithm of the probabilities. Before, I don't know whether you remember, the graveyard, the law is slightly different. The minus sign is missing. Anybody knows? I mean, I'm not very good in keeping minus signs. You saw it already. Did I miss a minus sign, or did I confuse something, or where is the minus sign hidden here or there? Or did they miss it on the graveyard? I mean, that's a point one has to often, if you go through examples, you often get lost with different minus signs. In principle, I prepared an example. We come across these minus signs. So I use probabilities. And probabilities are something normally between 0 and 1. Yeah? So they are smaller than 1. So the logarithm of a number smaller than 1 or between 0 and 1 is negative. Yeah? So these minus signs cancels out. So my entropy is positive. The probability for a certain configuration is just the inverse of the number of configurations we have. Yeah, so if I have 10 possibilities, yeah, the probability to take one is 1/10. Yeah? And here, this W is a number of possibilities. So that's where the minus sign is just the inverse. But that's something one has to bear in mind if you play with these things here. So here it's the probability, and if you count the numbers, we have to omit this minus sign. So I don't know whether you use the same playing cards as we do in Germany. We typically have card decks with 32 cards. If you have them all in a series, probability is 1. Or number of possibilities is 1. If you mix them, how many possibilities do we have? It's faculty of 32. So we can, as a last remark, we can go through this example. faculty. And if you want to calculate this on your calculator, perhaps it just works, but normally it's overflow. But there is this very simple formula. Perhaps I should use an uppercase for the number of possibilities. Everybody knows this approximation formula. It's Stirling's formula. N ln n minus n. And 32 times Boltzmann constant times ln 32 minus Boltzmann constant. And that's something you can do on your calculator. So, and it's a small number, so the change in entropy is not that large. Typically, by the way, it's very practical to calculate or to give entropies in multiples of Boltzmann's constant, or if you have a mole in multiples of the gas constant, yeah, of R. But this is the change in entropy if you mix a deck of cards. And this also explains that it is very improbable that after mixing your cards, you have them perfectly ordered. Yeah, just given by this 1/32 faculty. Yeah, I think I stop here. It's a good point. I think I prepared some slides about a kind of application, but perhaps you know it. Here, this very simple model for ordering in a crystal. You have a BCC lattice with two species. And this is a real case, for example, in alpha brass. Below a certain temperature, the copper atoms go to one lattice side, for example, to the cube center, and the zinc atoms go to the corner sides. At a temperature, I think it's about 400 something. They are equally distributed. And you can, just using these approximations, here's the Stirling approximation here. That's where you have to be careful about the minus sign. Then you can derive an order parameter or free energy for the order parameter and the phase diagram or the phase transition. Yeah? You find that here for low temperature you have perfect order. That is all the copper atoms sitting on the phase, the body-centered sides and the zinc atoms on the corner sides. And here above this temperature, you have them equally mixed, and in between this order decays gradually, and that's what we call a second order phase transition. So these things one can easily go through with these points here. Perhaps we can go through it in one of the tutorials or so if anybody is interested. But to resume, I mean, this entropy is basically what is behind many applications in these atomistic models, explaining why, for example, in in the simple Monte Carlo simulation, at elevated temperature, the atoms spread equally over the lattice sides. At lower temperature, they form these clusters, because at lower temperature, I mean, there's one step missing, the free energy. But probably you know it's internal energy minus T times the entropy. So at low temperatures, energy wins. At elevated temperature, entropy wins. Yeah? And that's basically what you should try to understand here. Okay, so I think we close here. I stop the recording.
So good afternoon, and we are going to change gears a little bit. And we will start looking at some codes and some implementation details and things like that. you will probably be able to make some connection to the statistical basis. That will also happen as we go along, but it is always a good idea to also do some coding, some programming along with knowing the theory. So, we have arranged it in such a way that 2 hours of lecture and 2 hours of tutorials every day. So, the code that we are going to write or the script that we are going to use is for a simple Monte Carlo. Okay. I am going to do these things. We will look at random walk first and then we will look at Monte Carlo. There are 2 types of dynamics, one is called Glauber, the other one is called Kawasaki. I will show you what they are, and for both we will use the Metropolis algorithm for the Monte Carlo. I will show what it is. One of the important things that we have to do is to use periodic boundary conditions. That is because the number of atoms that we are going to deal with in our simulations is very small, and so if you do not use and if you leave them free, then you have a boundary or a surface, and the number of atoms that are sitting at the surface compared to the number of atoms in the bulk is very large, as compared to a real system where you will see very small fraction of atoms which are sitting at the surface. So, to get rid of this effect, typically we put periodic boundary conditions and get rid of the surfaces in the simulation cell. Sometimes people mistakenly say that using periodic boundary condition is equivalent to taking an infinite system, which is not true. It is a system which does not have surfaces, but that does not make the system actually infinite. So, typically in these simulations you will see that you have to also look at finite size effects by doing scaling studies. We will not go to those details, but we will at least look at what periodic boundary conditions are and how it is implemented for this simulation, this Monte Carlo code. There is a generalization to what is known as Q state parts model. As you learnt this morning, the number of atoms that you look at in a typical grain 50 microns could be 10 to the power 15, but there are Monte Carlo codes that are used to look at grain growth. Okay. So, what type of models are those? So, you will see that even though Monte Carlo is an atomistic model, there are generalizations where each Monte Carlo lattice point could represent something more than a lattice, and each lattice point might not be one single atom or one single molecule. It is possible to have a more generalized version, and one of them is known as Q state parts model, which is very important, which is also something that is used towards the later part of this course. We will use such parts models, and so it is important to know what they are. Then I want to end with a small note about random number generators on computers, because if you want to do any statistics, if you just want to get nice pretty pictures, you do not have to worry too much about what random number you are generating using to do these simulations. But if you want to also get statistics out of your simulations, then it is very important that the random number generator that you are using is nice statistically speaking. So, to do that, then you need to understand what are the random number generators that are available, which ones you should use, how do you choose, and so on. So, we will have a small note on random number generation in computers. I will point out to certain pointers, to certain literature that is available online free, you can go look it up. So, that is what we want to do in this session. Again, at any point you have any question, please feel free to stop me, and we will have a chat. So, let us start with a random walk, and the problem I have in mind is something like this. We will consider a one dimensional system. So, let us say that I have a vacant site, and let us say that this is a lattice, and so at equal distances, let us say that that distance is S, and let us say that this is the origin to begin with. Then I toss a fair coin, and if it comes head, I go here. If it comes tail, I go here, and I keep doing this exercise, right. I can take, let us say, n steps, n times I toss the coin, a fair coin, which means it has a probability of coming head or tail 0.5. So, if I toss, and with every toss I take a step, if it comes head, I go to the right, if it comes tail, I go to the left. if you do this, and many of you might have done statistics, what is the expectation value for S? Expectation value meaning if I do it very large number of times, n is not some number like 10 or 100, let us say that is a million or a billion. If I do, what do I expect? What is the average or mean after such large number of steps? 0, right. So, you expect, your expectation is 0. You do not expect to move from your point, right. 50% of the times you would go to left, 50% of the times you will go to right, and you will be there. But as many of you know, you have done statistics, average is only one of the quantities, but it is not the quantity or only quantity, right. You can also calculate expectation for S squared. It has a specific name in statistics literature. Do you know what it is? What is the expectation of S squared called? That is, we calculate S squared and we calculate its expectation. Variance, right? It is called variance. You can calculate the variance. The expectation is 0. What do you expect the variance to be? You expect it to be 0? No. What would that be? This is one of the strange cases where if I am doing it in 2D, it is far more easier to do. So, it is one of those strange cases where if it is 2D, it is far more easier for me to solve, to take the expectation value. What happens in 2D? I can take this to be a vector S and I dot it with S itself, that is what gives me the S squared, right. Right. Now, S dot S is what? Mod S cos theta. Theta is 0 or 180. So, which will give me plus or minus, that is why expectation value is becoming 0. So, now if I take the S squared and sum, so it is sum I equal to 1 to n, sum I equal to 1 to n, Si dot Si. So, n S squared will come out plus 2 n S cos theta Ij, which is plus or minus. So, that averages to 0. So, the expectation happens to be, the variance happens to be, the expectation for S squared happens to be n S squared. So, if you take 10 steps, right, there is a possibility that very small, right, all of them coming as head. So, that you will end up at 10 points to the right, all of them coming up as tail, which again has very low probability. So, but it is there, it is definite, it is non-zero, it is finite, it is very, very small. If you go to larger and larger numbers, that is still smaller and smaller. On the other hand, how many of them will give more or less nearly equal to, like if I take 10, 6 and 4 or 7 and 3, the number of possible ways in which you can achieve 6 and 4 or 7 and 3 are much more, right. That was the argument just now we had about most probable states are the ones which you will see. So, if you take 1 and so it will take randomly some 5, 6 on this way, 4 on this way. So, you will end up quite close to 0, but you will be slightly away from 0. So, mean tells you where you end up, it is a number, but variance tells you how many times you will be away from that and how far away you will be. Okay. Now, this distance that you travel from the origin or that vacancy travels from the origin is basically the diffusion, right. You put one vacancy, after some time you see it would have moved a little bit, and depending on how many jumps, we also discussed the number of jumps that atoms will make and so on. So, you give large amount of time, there is a very large number of jumps it would make, and even if you assume that all the jumps are equal, right, we looked at 1D, you can look at 2D, you can look at 3D in a simple cubic lattice in 3D for example, all jumps to left, right, front, back, top, bottom, all of them are equal. Thanks Subhash. So, you will find that finally, you will be away from the starting point, and how far away you will be is decided by the diffusivity, which is basically because of the random walk, right. So, even if you make a random walk, you will move away from the starting point, and that is simply because of the variance. And there are many scenarios where you will find this kind of expectation 0 and variance to be non-zero, and we discussed temperature. Temperature is another quantity. If you take an ideal gas, if you look at the velocities of the gas molecules and in any given direction, the net velocity should be 0, the average should be 0, otherwise the box in which you have kept the molecules will start moving, right. You cannot have any net velocity. So, the expectation value for velocity is 0, but the variance is not 0, and that is what the temperature is a measure of that variance, right. Higher the temperature, higher would be the spread. So, okay. So, this is a random walk, and you can see that where did we introduce the statistics in our coin toss. Whether I go to left or right is determined by the coin toss. So, there is some probability or statistics that is introduced in the process, right, and you saw that probability is closely related to entropy. Okay. So, you will see that we are always making these moves, or in our algorithms there is a random number that is generated, and then that is used to calculate some quantity, or some quantity is calculated, it is compared with a random number and so on. You can make the walk biased, by the way, right. You can toss a coin which is not fair, your expectation value will also not be 0 then. You will either end up to the left or right depending on what the bias is, and in real systems such biases can be there. It can be an ion which is moving, so there could be an electric field which biases, it could be stress field which biases, it could be temperature field that biases. So, all those will be equivalent to a random walk in a with a biased coin. So, you will have a definite tendency to move in one direction or another, okay. That is also possible, but the scenario, and you can also think of steps not being of same size. Okay. I took a rigid lattice and said that only these are jumps that are possible. That is not the case in a liquid or gas. Okay. So, even though we took a problem which is very simple minded and it is a toy problem, the essential physics is captured. So, you can also extend it to other scenarios. Okay. You can do this exercise after we do, you can take the same code and you can change it, you can build it into 2D, and instead of taking specific step sizes, you can also choose step size from another distribution, right. You can take a Gaussian distribution with one given step size and with some variance, and you can try to move around, right. Brownian motion where a pollen particle for example is moving around is an example. I mean, it does not move the same amount, right. It makes random movements, maybe larger steps, smaller steps in random directions, and it will also lead to a net movement of the particle, right. Again, that is where again Einstein comes, and that is why that relationship is called Einstein relation. Okay. Okay. So, this is the introduction to the random walk part, and next what I want to do is to show you a very simple code. So, I am going to load a package called statistics, because I am going to use a random number generator from a specific distribution, from the uniform distribution I am going to generate. This is the uniform random number that is generated between 0 and 1. To have this command uniform random number, I need the package statistics. Okay. So, that first line is loading the package statistics in Octave. Okay. Is equivalent to introducing some library or including some library in your C program. Then m is equal to 100. Okay. What I am going to do is that I am going to do this exercise of random walk 100 times. Each time I am going to start from here, each one is a sequence. I am going to toss the coin. How many times I am going to toss the coin? I am going to toss the coin 100 times. So, n is equal to 100 means for each random walk I am going to take 100 steps by tossing a coin, by deciding whether I move to the left, right and so on, and I do this exercise 100 times. So, that is why the other 100 is there. So, this loop goes from 1 to 100 means 1 means it is the first random walk, 2 means it is the second random walk, 3 means it is the third random walk and so on. So, I am going to take 100 random walks starting from the same point 0, and each random walk has 100 steps, that is why n equal to 100, and you can see I is 1, S1 is 0, that is my starting point. And then what do? I take a uniform random number. Uniform random number means it has the same probability for any number between 0 and 1. And so, if it is less than 0.5, I am going to take s plus 1, if it is greater than 0.5, I am going to take s minus 1. So, which means 50% of the times I will be taking a step to the right, 50% of the times I will be taking a step to the left. That is because I am taking the uniform random number and using that to do my step. So, that is exactly the process that I described here. I go here or there depending on what is the coin toss. Okay. Instead of coin toss, I am using a uniform random number, and that generator tells me whether I go to left or right. So, I have now stored in S of I, it is a vector, I is the step 1, 2, 3, 4 etc., and what is the point at which I ended up on the lattice is basically S of I. So, I can plot S. So, it will plot, and I am going to plot it with a circle, and I am also going to connect it through a line. So, I can see what the random walk is, and I have given some big marker size so that it looks nice on the graph. Okay. So, this end for is for the walk, this end for is for the different random walks. Then I will look at the somewhere in between there is a hold on. Yeah, this hold on is because it will plot on the same plot. Okay. Just to understand this better, let us do just one random walk of 100 steps and look how this looks, right. Okay. Can you see? Right. Started from 0, went to -1, then went to 0, then went to 1, then went to 2, and then came all the way back down, then it crossed 0. Okay. That is why sometimes you see in literature people will say that you take large number of times, infinite number of times this particle will cross 0. It will keep going up and down and keep doing for larger time, it will keep doing that. But finally, it ended up at a distance of -5, ended to the left at 5 distance, right. This is one random walk. Of course, I can do let us do 3. Okay. So, let us see how that looks. Okay. One of them ended here, the other one ended there. Okay. You can see 0 we started, it looks like some 25 it went, and this one, and only one of them went to this side and it did not go too far, right, can happen. Now, let us run actually what we wanted to run, it is going to take some time. So, I am going to take 100 random walks with 100 steps, and I want to see how this curve looks like. Okay. So, it will come in a while, but in the meanwhile, how many of you have worked with Octave or MATLAB? Is there anybody here who has not used Octave or MATLAB? You have not used, okay. You also have not used, okay. So, it is a good idea to Octave works on Windows machines also, you can MATLAB also works. So, you can, and you can do all these commands will work on MATLAB also. Octave is basically a open source replacement for MATLAB. So, you do not have to pay, you can use, and so you will be able to have this running on your MATLAB also. Okay. And all the code that I am going to show, at least in the beginning today, will all be in Octave MATLAB, so that you can understand what is happening without worrying too much about syntax and things like that. At the end, I will try to show you an code for Monte Carlo in C, and I have also shared in the directory the Fortran codes that Ferdy was referring to. Those codes are a little bit more sophisticated, okay, in the sense that they also, the visualization is also built into the program, okay, using X11 libraries, and it has nice visualization. So, I will also show you the visualizations. Their visualization looks much better than what I get in Octave, okay, but primarily it is the same thing. And the reason why we are doing Monte Carlo, yes sir. Yeah, I gave a slip in the morning, the link is there, Google Drive. If you go there, they are available. You can download the other codes also, so that as I am discussing, you can have them on your computer. Let me check if I have the. I think I sent an email to all of you, right? Okay, let me locate. If I have that, then I will. This is what the variance means. You could end up, you calculated ns squared, so you could end up on any of those points. Okay. So, square root n times s, that will be the distance where you would end up. Even though the probability to end up close to 0 are much higher. So, if you actually plot this, you will see a distribution. The probability of ending up at those far away points are far less, and it is concentrated around the mean, because you expect the mean to be 0, your variance only is not 0. So, most of the times you will end up close to this, and you can see that even though it is a uniform random number and unbiased, but 100 is not a large enough number, right. Even if you toss a coin, even physically, you will not get 50 times head and 50 times tail. Okay. There could be a little bit of skewing, which is what you found in the, or which is what you find in this figure. So, there is a little bit of skewing. Is this clear? Do you have any questions? It's okay? Okay, very good. So, now let us move to a simple code to do Monte Carlo simulations, and let us see what we mean by Monte Carlo simulations. By the way, you can take this script, modify it to do a random walk in 2D, okay, and calculate the distance you end up with starting from 0, 0 to whatever point you end up with, right. How would you do a random walk in 2D? How many regions you can go to? X and y both, right. Either you can go to left, right, top, bottom. So, you will generate a uniform random number and you will give equal probability for all the 4. If it is between 0 and 0.25, 0.25 to 0.5, 0.5 to 0.75, 0.75 to 1. Depending on that, it will go to either left or top or right or bottom. Okay. You keep doing this, and that is, you will either add 0, 1 or 1, 0 or 0, -1 or -1, 0. You will add this to this and you will end up wherever, and then you will use this formula x minus x naught whole squared plus y minus y naught whole squared square root, that is the distance you would have travelled. So, you can do 100 steps again or 200 steps, and you can do it several hundred times and calculate how far away you end up from the point. So, that will be 2D. You can also generalize to 3D, it is not very difficult, it is rather trivial and so on. Yeah. Okay. M is the number of random walks that I take. Yeah. See, one random walk means I started at 0, I tossed coin 100 times, and maybe some 65 times it came head and 35 it came tail, and so the difference will give me where I end up with. But that is only one random walk, that will not give me the statistics, right. Now, I need to do it large number of times. So, M is that number of random walks I take, N is the steps in the given random walk. Is that clear? So, you can do the same thing in 2D and you can see where you end up with. Okay. So, that is as an exercise, just to fix the ideas and just to think about it, and also modify the script a little bit to get used to and so on. Now, let us talk about Monte Carlo simulations. Again, it is one single slide where I have tried to summarize everything, and then we will go to the code, and probably you will understand a little bit better with the code, and then we will run the code for some conditions. So, that will help us understand a little bit more better, and then you will play around with these scripts for yourself by putting different values and so on. So, to get a much better understanding of what is happening. Okay. Okay. So, what is a Monte Carlo simulation? The algorithm goes something like this. First, we generate a lattice. Okay. That lattice could be square or triangular, and Ferdi's code in Fortran is written for triangular lattice. The one that I am going to show you is going to take a square lattice. So, we take a lattice, that is the first step. Then we populate the lattice. I can populate with A atoms and B atoms. Right, that is one way. This is A and this is B. Okay. A or B atoms. I can also populate it with up spins and down spins. Okay. What is the difference between A atom, B atom and up spin and down spin? Why am I using the word spin and atom? What is the difference? Conservation, right. If I put A atoms and B atoms, the number of A atoms and B atoms cannot change, right. Mass has to be conserved, which means if I start with 10 A atoms, there had better be 10 A atoms at the end of the simulation. On the other hand, if you have spin, there is no necessity that it has to be conserved. All the spin can align along the same direction and get the sample can get completely poled or polarized, can happen, right. So, to distinguish between whether I am dealing with conserved quantities or non-conserved quantities, we use the word atom or spin. If you deal with spins, for example, then you can see in the dynamics also there is a difference. I can go to any of the sites and then just flip the spin, because I do not have to conserve, right. I can go randomly change one of the spins to down to up, that is allowed for me to do. If you do the flipping of the spin at a random site, that is called Glauber dynamics. That means Glauber means it is not going to conserve the spins. You keep adding the spins at different times, you might end up with different amounts of up spins or down spins in your system. On the other hand, if it is atoms, then only exchange is allowed. which means I pick a random site and I pick a random neighbor and exchange this atom with the neighbor. If you do that, that is known as Kawasaki dynamics. Okay. So, the Glauber and Kawasaki just tells you whether you are dealing with spins or with atoms, or you are dealing with non-conserved quantities or conserved quantities. If it is non-conserved, you can randomly go change. If it is conserved, only exchange is allowed, so that you do not lose the number of A atoms and B atoms. Yeah.
So, like when you say we have to exchange an atom with a neighbor, so like if
With a random neighbor, yeah.
okay, so like that neighbor can be a random neighbor and not necessarily like nearest neighbor.
It also has to be a nearest neighbor. In fact, in real systems, it does not exchange with the nearest neighbor, it jumps into a vacancy and some other atom comes into that vacant site, and so vacancy moves. But we are not considering a vacancy mechanism of diffusion, but we are considering an exchange mechanism of diffusion, like you saw in the blues and reds this morning, right. It was bonding, these two solids were bonding by forming a region which had composition all the way between this red to the blue. They were doing that by exchanging, right. I cannot take a blue atom and exchange with something far away. I mean, in principle on the computer you can do, but that is not realistic in the sense that the interface will not form the way you saw, right. We will not be simulating that process. That is why you have to choose a random site and with one of its nearest neighbors chosen randomly, right. You cannot choose always the right or left. Yeah. Let us say that this is the random site that I picked. It can only exchange with these 4. You cannot exchange. I mean, there are codes in which they also allow second nearest neighbors, for example, to exchange, because I mean sometimes this can give rise to very high anisotropy. So, sometimes people do nearest neighbor, next nearest neighbor, second nearest neighbor and so on. Okay. Yeah, Ferdi, you had.
I think one must make a little restriction. This depends on what you are aiming for. I think we have 2 lectures on this. There's, I would say, the general Monte Carlo to, yeah, we say to efficiently sample the configuration space, yeah, to calculate equilibrium properties. And that does not matter which type of algorithm you use. Yeah, I mean, if you just want to have all available configurations with the proper probabilities, then you can do for exchange, for example. Yeah? But here in this example, and that's most of the applications we are interested in, is the temporal evolution of a system, the kinetics. And if you are interested in the kinetics, it's becoming very important what type of elementary kinetics to choose. If you choose distant neighbors to exchange, the kinetics is completely unrealistic. For example, the growth of precipitates or segregation to defects or whatever. Yeah? While if you are just interested in equilibrium properties, like how many atoms segregate to a certain defect, yeah, then you can do what you like, and which is the most efficient then.
Yeah. To add on that, in that blue-red case, suppose you are interested in the final state, which is, let us say, well mixed state. Then you can exchange randomly whichever way you want, and you will finally reach a state where all of them, red and blue, are randomly distributed on the given lattice. But if you are interested in this interface forming and how it is spreading and so on, then you have to use one of the physically meaningful moves. Okay. There again, one might argue that second nearest neighbor jump is not physically realistic. Atoms will only jump to nearest neighbor and so on, but there are reasons to do. And if you want to avoid this kind of anisotropy that is coming from the lattice, etc., triangular lattice is another that you can use, which is also allowed. Okay. Any other question?
So what is spin? What is spin and what is conservation of spin?
Okay. So, you have heard of magnetic systems. So, where does the magnetism come from? You have heard? Yeah. So, iron, for example, you take this stuff called spin, if they are all aligning, then that is why it has this magnetic property. And you have also seen, or probably did this as a kid, that you can take another piece of iron which is not really magnetic, and by doing constantly rubbing it against, you can make it magnetic. So, what is happening there? Initially the spins were not aligned, but you are aligning them. Can also happen in ferro electric materials, it is called poling. Under an electric field you can make sure that they are all aligned the same way, which means they do not have to be conserved, right. You started with spins are all aligned in different direction, but you made sure that all of them got aligned in the same way. So, initially maybe they were up and down, let us say only 2 spins, and some region had down and some region had up, or all of them randomly distributed. Finally, you can make all of them up or all of them down, right, that is allowed. On the other hand, if you have 50% A atoms, 50% B atoms, you cannot make the 50% A atoms into B atoms. In a closed system like this, I mean, you can also do that if you allow for exchange, and B atoms can go instead, A atoms can be replaced and so on, right. So, in other words, when it is conserved dynamics, typically we use the word atom to indicate that this has to be conserved. When it is non-conserved, typically we tend to use the word spin. But that does not mean that spin refers to only spin. Spin can actually refer to the atoms. That was the last example that Ferdi was showing, where he was talking about copper zinc, right, or nickel aluminum, which has an ordered structure, where you have a BCC structure and you say that in the ordered state the body center is occupied by one type of atom and cube corner is occupied by another type of atom. You can say that this is up spin, this is down spin, for example, because that site being occupied by that atom, if you can represent, I mean spins are represented, or in the code you will see it is all represented by 1 0 or 1 minus 1 and so on. So, you can have, in this case it is allowed, because like he showed, at some temperature you will see that any atom can be in any position. Okay. As you go to lower and lower temperatures, then they will start doing this. There will be nice alignment of up spins along one and down spins along the other and so on. It will also form the so called variants. I do not know if you know about these ordered structures, that antiphase domains and things like that, right. So, it can, in one place the cube corners will be by these circular atoms, in another place the cube corners by these crossed atoms, and so when they meet you will have a boundary which is having. So, all that you can model using the same Monte Carlo code, where you are now no longer conserving the, we are not now giving the meaning that it represents A atom or B atom. We are talking about the occupancy of a given type of site by A or B, which can again be non-conserved. With 50% probability it can occupy that site, 90% probability it can occupy, 100% probability it can occupy. 100% probability it occupies that site is completely ordered, 90% is somewhere in that region where it was falling, and after it hit 0, all sites are equally probable for all the atoms, right. So, even though we use the word spin, that it comes from this, and the typical model is from which it comes in statistical mechanics is known as Ising model. Okay. Q state parts model is a generalization of Ising model. Ising model talks about only up and down spin. Okay. So, that is the sense in which we are using the word spin. Is that clear?
I think it is mostly because of historical reasons. Yeah. These models were developed when people try to understand magnetism. So, and then material scientists stole these ideas and adapted these ideas, and they kept the words without the meaning.
Okay, is that clear? Okay. So, now you do the exchange or flip, and again as it was discussed just the earlier lecture, if you were at 0 Kelvin, the system should choose a state where it has minimum energy U, right. So, any exchange or flip which increases the system's energy is not allowed. Okay. Spontaneously a flip would happen only if it reduces the energy, but that is true only at 0 Kelvin. At any temperature above 0, entropy is trying to destroy this order a little bit. Higher the temperature, it is trying to destroy more. There is a temperature where entropy will completely take over and will completely destroy the order, right. That is why in the order disorder transformation also, what was ordered at low temperature became disordered at the higher temperature, which is the same thing that happens in magnetic systems also, right. Curie temperature is the temperature where the spins are no longer ordered, it will no longer be ferromagnetic, it will become paramagnetic, right. So, same thing can happen here also, the system can go from ordered to disorder or disordered to order, or we had the other case where Ferdi showed these precipitates forming, clustering, coarsening and so on. So, it is a phase separation, all A atoms came together, all B atoms came together and formed these regions, but if you go to higher temperature they will all mix very well, and beyond that if you go it will become a liquid and get completely mixed, or sometimes there is also immiscibility in the liquid state, you still go to higher temperature they will also start mixing. Okay. So, at any temperature which is non-zero, our algorithm is like this, if the flip or exchange reduces energy we accept it. If it does not reduce energy also we accept it, but accept it with a probability which is given by this exponential minus delta E by kBt. Okay. The kBt is a hint that this is mimicking what entropy does to the system. Okay. This algorithm is known as Metropolis algorithm. This is not the only algorithm, there are other algorithms, but Metropolis is what I am going to show you. Okay. Today we are going to do a very simple Monte Carlo, Glauber Kawasaki using Metropolis algorithm. You will understand this little bit better probably at the end of this course, because we are going to do several such things and you will see what it is doing, and you will also get more physical feel for it by changing the kBt term. Okay.
Tomorrow I will also speak about this probability factor. Yeah. I mean, probably many of you know it, the Boltzmann factor.
Yeah, Boltzmann factor, right. So, I do not know how many of you have done MC or have heard of MC. You have heard of MC. You have done some MC also.
We have done Gibbs ensemble.
Gibbs ensemble. Okay. So, for the rest of you, what we are trying to do is that we are trying to mimic how a system, because of entropy, is exploring states, and those states at that moment might look like causing an increase in energy, but what the system is trying to minimize under these conditions is the free energy, which is U minus Ts. Like Ferdi said, PV term generally we neglect, which is true for condensed systems, which means solids and liquids, and there is a justification. If you take a look at Gaskell or some such thermodynamic textbook, they will show you that what is the contribution of the PdV term. A typical solid you take and the increase in pressure of 100 atmospheres for example can be achieved by changing the temperature by 0.1 Kelvin or something like that. Okay. In other words, the PV term is really negligible, so we do not have to worry about. So, U plus PV minus Ts is the right one, but U plus PV and is approximately equal to U, and so it is approximately equal to H. You can call it internal energy, you can call it enthalpy, whichever way. We do not worry too much about the PV term. We are only talking about the internal energy, which is the bond energy in this case. We are on a lattice, we are talking about AA, BB, AB bonds and the entropy contribution. We are not calculating the entropy contribution, we are just trying to make the system mimic what the entropy would do to the system. There is a way to evaluate entropy from here, okay, which will probably at a later point we will talk about, but that is not the point we are trying to make here. So, at this point I also want to know if any of you have done regular solution kind of models or what they mean field models for alloys. Yeah, no? Okay. So, these models are models where we do this kind of simple construction. Okay, take a lattice, take different types of atoms, assume that the AA atoms, AB atoms and BB atoms have some kind of bond interaction, and then we throw them on this lattice, and for calculating the entropy we make the approximation that these atoms are not interacting among themselves, they are independent, and so you can calculate the entropy. Like you saw in the probability argument, right, we assume that it is ideal, so they are not interacting, so you can, but that is not the case in real systems, right. If AA bonds and BB bonds are favorable to AB bonds, random distribution of atoms is not going to happen. So, in real systems the contribution that will come from entropy, because certain configurations are more favored and certain configurations are not favored, will be different from what you would get if you assume that all configurations are possible. But as you can see, it is much more easier to assume all configurations are the same and then calculate the contribution of configurational entropy, because the number of states that you have to count is far more easier. So, for real systems, if you want to evaluate these entropies, then you have to use these simulations and evaluate. This process is known as thermodynamic integration. To get the entropy primarily and hence free energy and so on is known as thermodynamic integration, which is something that we will discuss later, but this is where it comes from. Okay. It's clear? Okay.
Regular solution model
Yeah.
I showed at the beginning, I have on the end of my slides, so I can upload it, and if anybody likes, you can go through it, and if you have a question on it.
Yeah, if majority of you do not know this model, I mean if you want, we can also do a small session on that outside of this, and it does not take much time. So, it is pretty much there, same K ln omega works, and same Stirling approximation is used, and so on, it is trivial. So, we can do that, but take a look at it, and if you do not, because most of you are from chemical and mechanical, you told me. So, physicists would have done it, and they would have done it saying that it is a mean field model, and the metallurgists would have done it, and they would have done it calling that as a regular solution model. Yes, okay, more or less the same thing, but the others, if you have not done, we can take a look at it.
By the way, there is a certain parallelism, I call it the ideal solution model. If you neglect the interaction, and you know all, I guess, ideal gas model, which I also applied here. And basically they are the same, they neglect all the interactions, and also what comes out is very similar, yeah? Except that for the ideal gas model, if you want to calculate the entropy, you have to go some step into quantum mechanics, while in the ideal solution model everything comes out by itself. Yeah? So it's in fact it's easier, but the result is the same. Similar.
Okay. Any other question? Yeah.
Step number 5.
Huh.
Once we flip the spin, fifth bullet.
This one?
Yes.
Huh.
So once we flip the position of atom to the
No, there are two processes. One is if it is a spin, I will flip the spin to top, right, up from down. Now, before flipping, this had how many like neighbors? 2 and 2 unlike neighbors. It would have had some energy. Now, if I make it up, what happens? So, what will be the delta E? So, it does not matter whether you change it or not, right, but it could be that this was also up, then what happens?
My question was that how to calculate delta E.
So, you have to know upspin with upspin, is it preferred, or upspin with downspin is preferred? It is ferromagnetic or it is anti-ferromagnetic,
Physics.
right. That number comes from the system, right. AA bonds are preferred or AB bonds are preferred. In some systems they order, which means nickel aluminum, for example, nickel atom would like to surround itself only with aluminum atoms. So much so that even if you melt this composition, they say even in liquid state nickel atoms has more aluminum atoms surrounding it. Okay. But in some cases they want to completely phase separate. right, gold nickel for example. Same nickel, with aluminum it would like to surround itself with aluminum, you put it in gold nickel, all nickel would like to be by themselves, all gold would like to be by themselves. So, that interaction, what happens? So, he was talking about interactions, right, the interaction energies, pair interaction energies, which is the input into the Monte Carlo models like EAM potentials for MDE. This we have to give by looking at what is the system we are looking at. Okay. So, we will run different cases and I will show you what happens. Like, okay, I take a case where let us say up spins are preferred. I give the energies in this way and you will see that if I go to high temperature, it does not matter what you say, because energy is not the consideration there. So, it will always become random, but as you go to lower and lower temperatures, you will see more regions with up and up spins forming. Now, if you say up and down spin is preferred, start with the same configuration, you will see that it makes a nice chessboard, up down, up down, up down. Okay. We will see in the simulation, we will do that. Okay. It's clear? Now, this is some terminology. In Monte Carlo, if you have a lattice of size n by n in 2D and n by n by n in 3D, if you do this process, flip, calculate and accept or reject the flip n by n times, it is called one Monte Carlo step. Basically, because you are randomly choosing, you would have sampled all the points at least once, that is what it means. So, if you say 10 Monte Carlo steps, on the average every site would have been sampled 10 times, that is what it means. Okay. So, typically the measure is given in terms of Monte Carlo steps. So, we will say okay 100 Monte Carlo steps, 200 Monte Carlo steps. That does not mean that we did it only 200 times, but we did it 200 times the system size. Okay. That is what this terminology is. So, on a n by n lattice, if you make n by n such moves, that is called one Monte Carlo step. Okay. This is just terminology. You will see this and I will keep saying 1 MC and 2 MC step and so on. So, you should know what it means. Now, like I mentioned, periodic boundary condition is very important even from the algorithm point of view, because let us say that I did not have periodic boundary condition. Now, take this, suppose this site is chosen randomly. In global dynamics it does not matter, I am going to just switch its spin, but I will still have problem with respect to energy because it has only 2 nearest neighbors, right. The other 2 are broken bonds, that is what gives rise to surface energy. So, the energy considerations will be different, and if it is Kawasaki anyway I cannot exchange, I can only exchange with these 2, which is also a problem. Why is this a problem? Because you can see in this lattice for example, there is only one atom truly in the bulk, that is it has all the bonds satisfied. Out of the 9 atoms, 8 of them are on the surface, right. In a bulk system, if that is what you are trying to simulate, the number of atoms which are on the surface is going to be a very, very small fraction, most of them will be in bulk, right. So, in order to avoid that, we use periodic or cyclic boundary condition, sometimes it is called. What is this boundary condition? We take the system and wrap it back. Okay. These ones are 3 bonds missing, these ones have 3 bonds missing, okay, we connect those bonds. These have 3 missing on this side, these have 3 missing on this side, we connect them back. Or can also think of this way, because if you consider second nearest neighbors and so on, you can take this configuration, repeat it in all directions. Okay. So, this one will have as second nearest neighbor this and so on. Okay. On a larger lattice where you have much more number of atoms, sometimes if you need third nearest neighbor, fourth nearest neighbor and so on, with periodic boundary condition, then you know that this last one has this as the first nearest neighbor, next as the second nearest neighbor and so on. Okay. So, this is known as periodic boundary condition. Like I mentioned at the beginning of this lecture, it is to avoid these surfaces that show up in the simulations. Sometimes people mistakenly think that because there are no surfaces, the system is infinite in size. That is not true. As you can see, in this case, there is no second nearest neighbor. First nearest neighbor itself also is turning out to be second nearest neighbor. So, obviously, you will get everything wrong if you thought that this is equivalent to an infinite system. Okay. So, typical simulations that are done in Monte Carlo, there is called something called finite size effect, and to do that, to learn what it is or how much it is and so on, you do for different sizes and you plot the property that you are interested in as 1 by size, and then you can you will have data points, you can extrapolate the data to 0. 1 by s equal to 0 is equivalent to s equal to infinity. So, you can say that this is what an infinite system would have probably. Okay. So, no guarantee, but this is a process. I mean, sometimes if you want to know how much is the size effect, or is it very prominent, or have we avoided the size effect and so on. So, you will do this 1 by s versus this thing, and then the very close to the lower end you will see data points, and most of the times people take that to be a straight line, extrapolate and get to 0 and say that this is equivalent to what the infinite system size is equivalent. Okay. I do not think we are planning to do finite size scaling in this. Yeah. So, but you can look up, there are lots of material. We have not listed Binder's books, Binder and Landau. So, some of them have some of this stuff, they are more specific and sort of niche, but there are material that is available. If some of you are interested or some of your problems will take you there, you can go look it up. Okay.
About boundary conditions, periodic boundary conditions, where one has to be careful. For example, if you are speaking about a system with some internal order, like the one who showed there, like the copper zinc system. Now, if your system size is odd, so only 9 atoms or 99 or so, then you put the periodic continuation on the side, and you create an antiphase boundary, an ordering defect, and often you don't see it because you don't look at the periodic images. So these are things one has to be careful about. If you have long-range superstructures, that your periodicity is compatible with your structure you are looking at. That's one point one has to be careful. And then in molecular dynamics, we don't work on a rigid lattice, but we have lattice distortions. So, for example, if you put a dislocation into your material, one dislocation, one edge dislocation, accelerating your crystal now looks like this. If you continue it, you have a gap here. So again, you have to be careful. Either you don't use the periodic boundary conditions in this case, which introduces some strange effect sometimes, or you use at least 2 dislocations, one with Bogas vector like this, or like this, and the other one like this, dipole. And same with grain boundaries. Tilt grain boundary also distorts your lattice. So always you have to be a bit careful and check whether the boundary conditions you use here, these periodic boundary conditions, might influence your result. And of course they should not. Yeah. So it's sometimes a bit tricky.
The funniest mistake that I made, take a box, I want to have these 2 precipitates as far away from as possible.
Right, yeah.
And then because of periodic image, they are just sitting next to each other.
I had this problem with the ordering. I was studying, I forgot what, but some kind of more complicated ordering, and this was not compatible with my periodic boundary conditions. So I always created defects without seeing them.
Okay. So keep this in mind, periodic boundary condition is not infinite system. So that it just is repeating these boxes, and so most of the times you will be able to think about, but having said that, I mean we all make these mistakes. So just that you have to be aware, and if you see strange results, then you should know where to go look for what could be the problem. Okay. So, let us do some Glauber dynamics again using octave, and again it is a very simple minded code, and you will also see that the code is not very efficient, because sometimes there are tricky things that you can do which will make the code very efficient, but for first time learners those things are harder to follow and so on. So, I have written a very straightforward simple minded code. It is not very efficient, but it just gets the job done, and you can see how it works, and because it is in octave it also does the plotting. So, again load statistics, because I think I have a uniform random number somewhere. Okay. So, that is just for that purpose. So, I am taking a 64 by 64 lattice. There are 64 x points, there are 64 y points, and I am creating a linear space which is nx by nx and n by ny by ny. Okay. Lin space in octave is basically a vector. Okay. So, you can think of it as I have a matrix, I have labeled the top and I have labeled the side, that is what they are. Then I am creating a matrix A which is filled with zeros, which is of the size nx by ny. Okay. Now, my overall composition is 0.5, that is overall number of up spins or down spins is 0.5, or overall number of A atoms or B atoms is 0.5. So, that is what C0 means. It is given the name C0 because it is like composition, okay, composition of the beginning, that is why C0 simulation beginning. Okay. Now, because I want to now, this is what I said, first thing is to create the lattice, right. You have created a lattice, A is the lattice. The second step is to populate the lattice. How do I populate? I want 50% upspin or 50% A atoms. So, I go to every site, I toss a coin, if the coin is giving me head, I will put A, if it is giving me tail, I will put B, which is what is being done here. See, it is already populated with all zeros. In other words, it is equivalent to saying that I have now have all A atoms and 50% of the sites I am going to turn into B, or all of them are up spins and 50% of the sites I am going to randomly choose and make them down spins. That is basically what I am doing. So, I generate a uniform random number. C0 could be anything, in this case it is 0.5, it could be 0.4, it could be 0.3, and the uniform random number has the same probability for all numbers. So, if you take that it is greater than or less than, it does not matter whichever way, you make it the other value. So, as you can see, the A or B or up or down is being represented by 1 and 0. I have to interpret 1 is up or 0 is up, I can give whatever meaning I want, or 1 is A or 0 is A, whichever thing I want to I can. Okay. In this lattice there is no vacant sites. Sometimes you also do simulations by introducing one vacancy. There again the system size becomes important, as you would know or most probably would know. At melting point, most of the materials will have vacancy concentration of the order of 1 in 10,000 atoms. 10 power minus 4, 10 power minus 5 is typically the vacancy concentration. So, which means if you are doing a Monte Carlo simulation, unless you have 10 power 5 atoms, you cannot introduce one vacancy if you are doing the simulation at melting temperature. Okay. Come to lower temperatures, it is still smaller concentration. Sometimes you do not even have that many atoms in the simulation cell, maybe you are doing at 300, maybe the vacancy concentration is 1 in 10 power 8, you do not have 10 power 8 atoms in your simulation. Okay. So, you are introducing a vacancy will lead to artificial quicker simulations, because it is equivalent to having much larger number of vacancies, like in the aluminum copper that Freddy was referring to. The quenched in vacancies make the dynamics faster. So, here also you will see much faster dynamics, because you have introduced a vacancy which is much higher in terms of real terms, the vacancy concentration. Okay. Even though you would use temperature etc. 300, but effectively the kinetics will be as if you are at a much higher temperature, because the vacancy concentration is high. So, need to keep these things in mind. Anyway, we are not introducing a vacancy in this case. So, I just populated the lattice here. Is this part clear? create a lattice and populate the lattice. We did the population. Now, I am just calculating, right. You add them all up and divide by nx and y, it should come to about 0.5, right. It will not come exactly 0.5 because 64 by 64 is a small number. You toss coins, you will be near about 0.5, maybe 0.49, 0.51, whatever, depending on what you get. But anyway, that we do, and every step we print to know, because this is global dynamics. Remember, it does not have to be a constant. But the same exercise when we do with Kawasaki, you will see that it always remains a constant. If not, your code has a bug, you have to go check. Okay. So, for that purpose I am doing. So, this is not really part of the Monte Carlo algorithm, but one thing you should all do, I mean, you are not going to write your codes, at least not for this, we will use LAMPS, Sparks, etc. But whenever you write codes, wherever possible you should add these kind of checks in the code, and in C there is a way to make sure that these checks part of the code is not run for production run. Okay. There is a flag that you can switch on. So, when you are debugging and when you are first changing something, etc., you can see that all of them are in place. These are called sanity checks. You have to make sure that your code passes all of them. So, it is always a good idea to introduce them and keep them in the code. Only in the production run, then you can comment them out and not include in the calculation, because they are taking some resources and you might not want them. Okay. So, this mesh is basically a way to plot, right, x point, y point, and it will plot a value is 1 or 0. So, if it is 1, it will have some sign, if it is 0, it will have some sign. So, and then I look down on the mesh, that will show me how the lattice structure looks like, how the population looks like. Okay. So, this is just a way of visualizing for me in Octave. Like I said, I mean, this is not great visualization, but sufficient for our purposes. Okay. So, I have this value called inverse t here. See, there is exponential minus delta E by kBt. So, 1 by t is the factor, and I can normalize delta E by kb, also possible. Okay. Because otherwise you are going to be dealing with what do you think will be the change in delta E if they are bond energies? What is the typical bond energy order of? Assume some copper or assume some NaCl. What is the order typically? Electron volts, right. So, some 10 power minus 19 joules or something is going to go there, and Kb has 10 power minus 23. So, another thing when we are doing simulations, we always want to be in non-dimensional units where numbers are running from 0 to 1 and so on. Okay. So, you can represent delta E in units of kBt, so that you can make your temperature go from some 0.1 to 10 or something like that. Okay. So, most of the times these codes are written normalized like that to make life easy. I still do not know inverse T of 10 whether it is correct or not. I just wanted to give.
Delta E by kV, they dimension both, or delta E by kBt, the whole term is done?
The whole term is dimensionless because it is on exponential, right. This is energy, kBt is also energy. So, it is dimensionless. But if you take kb, which is 10 power minus 23, T is typically 300,000 whatever. So, it will bring it down to 10 power 21 or 20, and then you will have this also 10 power minus 19 of the order. So, you will have some exponential of 1 by 10 order quantity.
I think a very simple thing to memorize is kT corresponds to, or 1 electron volt corresponds to a temperature of 11,600 Kelvin, so roughly 10,000. So, if you just take 10,000 in the denominator, and energies in solids, most energies are around an electron volt, so defect energy, vacancy energy, and so on. So, this typical energy is 1/10.
This is just order of magnitude calculation. Like he said, I mean different systems will be different, but they are typically electron volt, right. So, okay. So in all these calculations, you will generally see numbers. I am not putting any units because I have non-dimensionalized them. So that Ferdy's the order parameter also he did not discuss in detail, but there also there was a non-dimensionalization that was done. The T by Tc, it was from 0 to 1 was where Tc was and so on. So, this is typical and this is how you should do. It is a bad idea to do simulations or numerical computations in dimensional numbers. Okay. You should try to non-dimensionalize as much as possible. It also gives you the advantage, you know, as long as this ratio is the same number, whether it is copper or silver does not matter. What happens in copper at some temperature maybe is happening in silver at some other temperature, but all that you will capture in one simulation. You do not have to do repeatedly, right. So, that is another advantage. So, okay. So, that is basically, remember this inverse T is basically the term that is going to go into my exponential calculation, that is why it is there. Now, I am going to run 100 Monte Carlo steps, right. So, this now shows you, okay, I have not changed it here maybe. No, I have done. Okay. So, k goes from 1 into nx into ny into MCS, right. 100 MCS means 100 times nx ny, that is what I should run. In the other code I have actually separated it out so that you will clearly see how I am doing MCS, but here I have not. Okay. Now, what do these two do? Generate a uniform random number between 0 and 1, multiply by nx minus 1, nx is the number of lattice points along x axis. So, 64, so 63 and add 1. So, what am I doing by doing that exercise, and I am casting it to an integer. I am picking a random point between 0 and 1 and 64. Similarly, I am picking another point between 1 and 64 in this case, because nx and ny happens to be the same, if ny is different. So, I am picking a random coordinate, random lattice point, random x and y. Okay. Once I have chosen, I am defining left, right, top, bottom points for that point, right. Left is minus 1, right is plus 1, top is minus 1 on the y side, sorry, plus 1 on the y side. Bottom is minus 1 on the y side, depends on where your origin is. This is how I am saying left, right, top, bottom for my system is. Once I do, this is where I am implementing the periodic boundary condition, right. Suppose I took I and subtracted 1 and I got a negative number or 0, that means probably I picked a point here. Only if it is 1, if I subtract 1 I will get 0. So, which means that is a point. So, to implement periodic boundary condition, what am I doing? If it is 0, if I add this length, I will get this point, right. This is one implementation of periodic boundary condition. There are many different implementations. Tomorrow when I show you the MD code, I will show you another implementation. It depends on how you shift. You can go 0 to L by 2, anything greater than L by 2 you can subtract L, and so you can go from minus L by 2 to plus L by 2. Those of you from physics will know minus pi by a to plus pi by a, you are always in the first Brillouin zone by going from with 0 in the middle, right. So, there are many different ways of doing it. The way I am doing it is, if I am going below 0, I am going to add the complete length, so that I will come on the other side. Okay. Now, this algorithm is more generic. You might have second nearest neighbor and so on. So, from 0 you will go to minus 1, you will add L, so you will come one step before. So, it automatically will take care of all of that, does not matter how many nearest neighbors and so on. Okay. So, this you can put, I only calculated L, R, T, B, you can calculate left of left, right of right and so on. Sometimes you might need them, even in those cases this algorithm will work. This part clear? Okay. So, we have taken a lattice, we have populated it with the given composition, we have chosen a random point, we have calculated its neighbors by calculating the making it consistent with the periodic boundary condition. Now, we are ready to calculate the E initial and E final. This is global dynamics, I only have to switch the flip the spin at the chosen point. So, I am going to first calculate the energy with the current spin, I am going to flip, calculate the energy, then take the difference, then I can implement metropolis. Is this clear? Okay, so, EI is 0 and I am going to calculate EI by calculating Aij is the point, with left what is the energy, with right what is the energy, top what is the energy, bottom what is the energy. Those are the 4 bonds that we need to. To do that I have to know the energies, right. This is the energy function. Okay. Remember, I took 1 and 0. So, if A equal to B, C is equal to 0. What does that mean? Same type of 0 0 or 1 1, then I am going to take the energy to be 0. The C is the what is returned, this function returns C, else I am taking C to be equal to 1. Okay. You can switch, you can make if A equal to B, C equal to 1, else C equal to 0. That will result in the opposite microstructure, right. In one case it will make all A's and B's collect together, which is known as phase separation. In the other case it will make complete mixing at the atomic scale, which is known as ordering. That depends on the energy. This answers your question, and I am putting 1 0 etc., because everything is normalized. So, this del E with KBT normalized in that unit is why I am giving these energies. Okay. Now, I can flip, if Aij is already 1, I make it 0, if it is 0 I make it 1, that is just flipping the spin at that point. I calculate the energy after flipping, that is the EF, I take the difference between the two, that is the del E, and if del E is greater than 0, I do this exponential minus del E into inverse t, because all that KBT everything is there, and I calculate that probability. Remember what was our algorithm? With this probability I have to pick, probability del E is exponential minus del E by KBT. So, I calculate this, I calculate a uniform random number, if this number happens to be less than that I accept, if it is greater than that I do not accept, otherwise I flip it back. So, the flip is not accepted. Okay. This is only if del E is greater than 0, del E is less than 0 I do not do any of this. So, which means I have already accepted the flip, that is the algorithm, that is the metropolis. So, this is the metropolis, this 4-5 lines, that is it, done. Okay. Once in a while I will plot, and every step I will also calculate the overall composition or number of spins. Okay. Is this clear? It is always a good idea to have this, my previous I had a hold on, so it is plotting on the same thing. So, what happened? Crosses are one type of atoms, and the yellow regions are another type of atoms. So, this system is clustering, it is collecting, it is exactly like the blue, the precipitation case that Ferdi was showing. They were coming out and they were forming small regions and they were coarsening and so on. Okay. Now, we can just go change, and you can see it is global, because the numbers are not constant. I started with around 0.5, so it is more or less near 0.5, but it is not a constant, it can fluctuate, it can go up and down, because I am randomly increasing some upspins or decreasing some upspins depending on the local configuration. So, this is happening. Now, let me stop this and do the other one, and you will see the change. So, suppose if I make this as 1, this as 0 and run the same code now. Okay. Temperature is a bit high, yeah. So, let me it is 10 already, but maybe. It is not very clearly seen for me, but the Kawasaki code shows much better, because I think there I have a plotting which is a little bit better than this. Okay. So, we can make inverse temperature very small, which would be equivalent to large temperature, then it should destroy whatever it is doing, right. Everything should be random. You can check that also, you have the code, you can check that also. So, let me just run through. I think my other visualization is much better, this is not coming out great. This is also better code, as you can see, documented. So, define the size of the lattice, define 2 variables for help in plotting, and initialize the lattice with A atoms, and overall alloy composition is determined. Remember, this is Kawasaki, so it is going to be, so replace C0 percentage of site with B atoms. So, composition is that of B atoms, and I calculate the average composition and print it, then I print the initial structure. This is where I am defining the interaction energies EAA, EBB, EAB, okay, and define temperature. So, inverse temperature of 1 here and 20 Monte Carlo steps, and I go NX, NY, MCS, choose a random site, identify the neighbors, implement periodic boundary condition, choose a random neighbor, choose a number between 0 and 1, 0.25, 0.5, 0.75, 1, depending on that it will choose which neighbor to exchange with. And remember, for energy now you need the nearest neighbors of the next nearest neighbor, right, understand. If I decide to flip these two, initial configuration, what is its energy, what is its energy, and I am assuming energy to be only nearest neighbor bond energy. So, only nearest neighbors are needed for both. Then after flipping, what is the energy? So, I need to calculate. So, you need the nearest neighbors of the nearest neighbors, which means you have to again calculate it consistent with the periodic boundary condition. Okay. So, that is what is being done here. Okay. If suppose these two sites are of the same type, exchange is wasted, right. I mean, it is not going to, both are up, you say another this up, that up, does not matter. So, you are going to, so we will only flip if they are of different type. Okay. So, that is what is being done. Then energy calculation, E initial, E final. One is for the atom with the neighbor with who you are flipping, and the other one is for the neighbor that you are going to use for flipping. That is the initial energy. and exchange the atoms, calculate the exchange configuration, and the same Metropolis algorithm here and calculate the average composition. Only thing I have to show you is the energy calculation. Suppose I decided to choose this atom and I decide to flip it with this. Its neighbor also will contribute to this energy after flipping, right. So, with respect to this site, its nearest neighbor and its nearest neighbor. So, it is like second nearest neighbor also will have a say on this process, right. You have to know, because suppose you chose this site, then for this neighbor that you have chosen you need periodic boundary condition, it has to be consistent with that, right. So that is why you need periodic boundary condition for that also. Okay. So this is the energy that it returns. Can you see what it is doing and why it is doing, how it is doing? See, A atoms was 0, right, B atoms were 1. So if A plus B equal to 2, that means it is a BB bond. If A plus B is 1, that means AB bond. If it is 0, that means they are AA bonds, and that is all. Okay. So it will return the bond energy. Okay. So let us run this. I think I have better. Okay, you can see composition cannot change, said approximately 0.5, 5127 is what it shows, and it will remain throughout. If not, I have to debug the code. This is Kawasaki, it cannot change. Now do you see what it is doing? Is it ordering or is it phase separating? I do not know. I tried to figure out somewhere I am not suppressing the output to the screen. I mean, you look at it, I do not know where it is coming from. If you can, one of the conditions maybe it is checking and it is still printing the answer. Yesterday for a while I looked at and then I couldn't, I said okay. Okay. Okay, can you see the checkerboard pattern that is showing up on the screen now? The red, black, red, black. So this system is ordering at the atomic scale. Okay. You can check that by changing the energies. Let us flip the energies. Let us make this see lots of regions where you see this kind of checkerboards. So now let us run this one and see what happens. Now again random number. So that time it was 0.51, this time it is 0.49, and now you can see that this is closer to what Ferdi was showing for the nucleation, clustering, coarsening. You can now go change the temperature. Now before I complete, you play with it, you come back tomorrow and tell me. Again we have a session tomorrow afternoon, tutorial session, we can have more discussions, or if you have faced any problem or if you have any issues with the code. I am also very notorious for giving wrong codes. Okay. Do not take any code that I am giving without any processing. Go through. The people have identified mistakes and have told me that I have given wrong codes. Once I gave a code for diffusion which was not conserving composition. Okay. So please do take a look at and come back to me if there are issues. Before we end.
Sorry, you might also try to optimize the code. There are certain rules which of course makes the code a bit more complicated. But for example, the calculation of the energy on each step probably not very efficient. Yeah? So you can make tables because there are very few possibilities. So you can make one table in advance and then just look up in the table which value you have to change, you choose, and so on. So if you take as much as possible out from the real loop, saves a lot of time.
Yeah. Okay. So, now in order of increasing difficulty, I also have given a C code. Okay. And if you have GCC, there is also a make file. The C code is called mc.c, and it does the same thing except for random number generator, which is the point that I wanted to tell you about. So, random numbers generated in the computer are pseudo random. If you really want to generate random numbers, you should look up for processes like ejection of some radioactive decay material or something like that, or go to a hospital and find out children born, male, female, etc. So, these are truly random processes. In India, children born could not, in some places might not be random, because people do interfere with this, but if it is not interfered with, then it is a random number. Okay. So, on computer we are generating random numbers, they are only pseudo random numbers, and so they fail after a while, and good random numbers which are also free are hard to come by. Okay. But there is this library called GNU Scientific Library, which is what I am using, and they have specific recommendation if you want to do simulations using some random numbers. Okay. If you go to the GNU Scientific Library manual, it is very beautiful and very interesting, very useful. Okay. So, they have some general comments on random numbers and so on, and then they say which ones to use for simulations if you are interested in statistics. Some Mersenne, yeah. So, you can see following generated are recommended for use in simulation. They have extremely long periods, low correlation, and pass most statistical tests. Okay. So, you can't, I have seen people using some RAND or whatever in C and try to do simulations. Okay. They will also produce microstructure wise, you will not know, it will also produce very similar looking, but if you do any statistics on that, that will not be reliable. And the recommended one, I used to use TAUS2, but now they have recommended this, and it has a period of 10 to the power 6000. TAUS2 has some period of 10 to the power 128 and something like that. Okay. TAUS2 is also listed as one of the recommended ones, which is what I used to use previously, but now yesterday I looked up and I found that TAUS2 is, there is a much better random number than this. Yeah, see, it has only period 10 to the power 26. The other one, that Mersenne twister whatever, is 10 to the power 6000. So, it is a really good random number, and if you are, especially if you are doing large number of MC steps and you are trying to take statistics out of this, you should use some such random number. Why are these, what are these? And there is this program called DieHard, which is used to test these random number generators and so on. So, this page is really useful, really interesting for those of you who are more interested. So, please do take a look at this generator, and you can go modify the scripts that I have given. Anyway, what I wanted to show you is, okay, so you have seen the MATLAB scripts, I have written a same thing in C, except that now the random number generator that I am using is using GSL, and I think I changed it to Mersenne twister yesterday, yeah, MT now, it is no longer TAUS, and it does the same thing, bond energies, and take this thing and for plot using GNU plot and making a movie out of it and so on. Same algorithm, choose a random site and choose its neighbor and make periodic boundary conditions and so on. So, it is no different from the code, you can think of it as just the translation into C of the MATLAB script that I have. Okay. And unlike the Octave script, here the data will come and it will be written to a output file, output directory, and if you use GNU plot, I think you can plot. GNU plot will load, and this is phase separating, as you can see. Okay. So, this is a C code. Okay. Now, for those of you who want to do a little bit more of coding, if you are interested, I have also given this nice code that Ferdy was talking about, and he has shared with me. So, it is in the same directory. It is called MC2D or something in my this thing. and this has a much better visualization. So, yeah. So, this is concentration, some of this is in German. So, probably concentration you think you can still understand. So, it is 0.5, temperature you can understand. I think this is scaled between 0 and 1. So, I will give something like 0.8 or something. Yeah. So, the visualization is showing some ordered structure with different variants, right, Ferdy? Yes. The different colors are variants. Okay. So, that directory has some 7 or 8 codes, all in Fortran, and these visualization is also written as part of the code using X11 libraries again. Okay. I do not know if when if you have loaded the developer versions of Ubuntu, I could just take it and run, even though Ferdy said it was compiled about what 10-20 years ago. Except for one, for which he showed me the command, that also I could compile. So, you will be able to compile and run. I am also giving this code because you can see the difficulty levels and you can see the kind of effort that was involved in doing atomistic simulations in those days. It is no longer true, you just run a script in LAMPS and open in Ovito, ParaView, and you can move around, you can see the dislocation and you can say this is a junction and so on. That was not the case. But those of you who are interested in coding and want to know the inner working and so on, it is probably difficult in LAMPS and Sparks because there is also this parallelization that comes in the way of understanding the code. Okay. But here is a Fortran code. So, in terms of difficulty level, you can start with Octave, then you want to have something slightly more complicated, go to C, which is just straightforward translation again in square lattice, but this is on a triangular lattice. And I think he also had a grand canonical simulation one.
If you lower the temperature, it's interesting here because I mean this is on a triangular lattice, so you have 3 different positions for the d atoms, 3 different types of ordering. Yeah, if you have 1/3 of the positions.
Shall I give 0.2 for D temperature? Ordered domain formation.
But there is one slight difference to Google's codes, which is a bit strange on the first view. I do not use periodic boundary conditions, but a slight variance. If you think of a square lattice, I mean, Google explains periodic boundary conditions, you just wrap the system around. It's slightly more efficient if you do the wrapping only once for the whole thing. Yeah? So you arrange all your square lattice on a long line and then you close this long line. So it's a kind of, if you look closer into a kind of helical boundary conditions. Yeah? It's just to save some time and have only one lookup. I mean, in Google's code you have 4 lookups for the periodic boundary conditions. In this case you have only one because you just close the system at one point. This slightly changes the situation, but I mean if you look at the code, perhaps you understand what I did at this time. The rest is very similar.
So, it also had one grand canonical. Let me run that and that will be the last one. So, we will conclude for this thing and what happened? I thought I clicked. I will give some concentration like 0.4 and this energy was scaled 0.2, 0.3. I will give something. Temperature is 0.8. Yeah. So, chemical potential. This was also scaled, no? But what did we have? 1 or something?
0 and then it's equal. So you get both equal probability, and now if you change to a negative value, I forgot which one, just make Ctrl C, then you get 1 species.
So, there are several codes here as you can see MC diffusion and MC random walk. One of them Ferdi was showing, right, on the side it also plots the box plot or the histogram and so on. Okay. So, all of that was coded in. Okay. So, this is next level if you want to explore, is also available. So, I am going to stop here. Tomorrow we will come back, we will take a look at a simple C code for doing molecular dynamics based on the algorithms that are described in Frenkel and Schmidt. Okay. So, some 3-4 algorithms are there, I have just implemented straight from the textbook, which is what we will look at tomorrow. Same way, I will show you the code, I will run, I will show the results, then we will do some tweaking here and there and see what happens to the simulation results and so on. Afterwards, we will move on to LAMPS. So, today and tomorrow you have to take help from Sushil and Nagarajan if you want to load LAMPS, parts etc. on your computers. We will do it only for Linux. If you are using Windows, check, I found that LAMPS, the pre-compiled executables are available. So, you can just download. If it is working, great. I will again share all scripts. You will be able to take the scripts, you will be able to run, and once you understand, probably you can go and use it for your purposes. Okay. Any questions you have?
Okay. One software package we did not mention, you use it as a GNU plot.
Huh.
I think for typical Windows users, it's available, but few know it. It's a very powerful, a bit awkward to use graphics package, just for XY graphics, but also for 3-dimensional. What I also like very much is the fitting procedure. I mean, here we don't need it, but it's a very stable fitting, curve fitting, function fitting algorithm implemented, much better than what you have in Excel or so. Yeah? So I always recommend my students to use GNU-plot instead of Excel. Origin is not that powerful in many respects. This GNU plot.
Okay, so this is also something I said I forgot. So we have so much to teach. Okay, so binary alloy A and B worked, and equivalent is upspin downspin worked. But if you have some of you, one of you mentioned some coatings of high entropy alloys or something like that. Yeah. So, if you have 10 atoms, how do I use this model? So, there is a generalization which is called Q state parts model. So, you start giving numbers 1, 2, 3 etc. and you treat them the same way that I am doing. So, it is a straightforward generalization of what is known as the Ising model. Ising model has 2 states and you can take it to Q states, and that is called a parts model. In the atomic this thing, it is the several different type of atoms. Of course, there is an equivalent non-conserved version to which you can think about the grains. Each grain is oriented one way, and you can take a general vector, let us say how the x axis is oriented with respect to the laboratory x. Different vectors will be there, and each vector is one state, it is no longer up or down, right, it could be any, and you can then build a model, which is what is typically used for grain growth, which we will look at in the second week. Okay. But that is called Q state parts model. So, if you see things like Q state parts model or something written, you know what it is. So, I am going to stop here.